Hello, grade 11s out there. Now, this is our fourth lesson on Euclidean geometry. So far, let's see how far we've traveled. We've looked at T, D, T, X, D, R, S, C. So we are left with P, T, and 1. Oh, lovely. So we are almost done with all the theory that we need to know concerning this theorem. So let's jump to P without wasting of time. What does P stand for? Parallel lines. Oh, this is a concept repeated over the years. Grade 7, grade 8, grade 9, grade 10, and now we are in grade 11. When we look at parallel lines, what are we looking at? We are basically looking at our fun angles, if you remember that. Okay, so let's quickly clear the air on the fun angles. F, U, and N. Mind you, the N could be in any shape. What we need to see is that these lines are parallel. Okay, now this angle would be equal to that angle. It's underneath, all right? And what do we call this? Corresponding angles. So we can just write corresponding angles. What about this one? These ones are co-interior. So A plus B would be equal to 180 degrees. Co-interior angles. That's our reason. They are supplementary. This angle here will be equal to that angle. And these are known as alternate angles. And we just write alt angles. We're done with parallel lines. It's not something new to anyone. So whenever we see parallel lines, we walk around your fun angles. And that's it. So it's going to come in handy as we look into questions where everything is now modeled up together. So don't forget, P for parallel lines. And that's simply talking about fun angles. This is actually the bedrock of any geometry that you would come across. So we're done here with that. We will see later how all of this play a big role. Now, what is our next one? The next one, what happened to my letter? It disappeared. Okay, I'm just going to type that in quickly. Let me see. It must be somewhere there. All right. So we are done with P. Let's go look at the next one, and that will be a T. Okay, everything just disappeared. I need to get rid of all of this. And we are now having a T. We have a letter T. Now, what is the meaning of T? T, we're going to be talking about a tangent. I remember we spoke about a tangent when we started. A tangent will not cut through the circle. It will only touch the circle once. So there's just a single point of contact. All right? A single point of contact. And that is going to be our tangent there. Now, when it comes to Euclidean geometry, what are we going to be dealing with when it comes to tangent? There are two things. All right? Number one, the angle between a tangent and a radius is 90 degrees. Oh, so we are saying that the tangent is perpendicular to the radius. Hence, we call it a tan rad. So I'm going to draw my radius, and this angle would be 90 degrees. Radius and tangent. The angle between a radius and a tangent is 90 degrees. It means that they are perpendicular to each other. The radius is perpendicular to the tangent. So you would hear us say tan rad, tan rad, tan rad, and that's what we mean, tan rad. That's the first one we need to know when it comes to tangent. I hope that makes sense. And when I talk about this, it also then means, check something here. If I take this line and join that, that then gives me what? A right angle triangle. So I need to consider a right angle triangle as well whenever I see tangent and a radius because of the 90 degrees. We're done with that. Remember we said tangent. There are two concepts that we need to look at. Now let's look at the second one. That's okay. Here we don't need to prove anything. Okay? We're not proving. Now the next one, still on the tangent, is known as tan-chord. This one is nothing to play with. It is a very, very important theorem. Tan-chord theorem, and you will be tested on this in terms of proving. Okay, so here's the theorem. The angle between a tangent, now you know what a tangent is, right? And a chord, can you see the word chord there? Is equal to the angle in the alternate. I want to write that in capital letter. In the alternate segment. And our reason for this, whenever we say this, is simply tan-chord. Okay, please, it is important also to know the theorem because there is what you call fill in the gap. Examiners are going to ask us to fill in the gap. Okay, let's look at the theorem in action now. So we have a circle and I have a tangent. Now that is the point of contact there. Okay, let's call this A, let's call this B, and let's call this C. We are going to then create an angle subtended. All right, watch this. And let's call this D and E. So let's go to the theorem again. The angle between a tangent, let me write my between nicely. The angle between a tangent and a chord, watch this. This is my tangent. This is a chord. Oh, there's an angle between them. Beautiful. Okay, please, I want you to watch this. Let's call this theta. The angle between the tangent and the chord. Let's call that theta. But I want you to watch something here. Remember that the chord divides a circle into two. So this is the minor segment and this entire thing is the major segment, right? So the angle we are referring to is in the minor. But then the theorem says that this angle is equal to the angle in the alternate. Let me add something here. The angle subtended by the chord. Let me just add something here, please. Sorry about that. Is equal to the angle subtended by the chord. Subtended by the chord in the alternate segment. Again, I'm going to write this in capital. In the alternate segment. So our angle that we're looking at is in the minor, the angle that it is equal to would be in the major. So, look at my chord. Chord BD is what we're referring to. Chord BD forms an angle E in the major. So we are going to call this theta. We are simply saying angle ABD. Let me clean that. ABD, that's the theta, is equal to angle E, and that is our tan-chord. Let's try something else. I want you to see something else. We could also create a tan-chord here on the other side. Tangent and a chord. So I'm looking at another chord here and another tangent here. Let's call this alpha. What do you think the angle, which angle do you think this would be equal to? Remember, this is now in the minus segment using this chord. This one also becomes the major. So we'll look at this chord. All right, where does it go to? Oh, it actually goes to D. That will give you alpha. Again, CBE angle will be equal to angle D. And both of them would have the same reason, tan-chord theorem. This we would need to prove because it is examinable. That we would need to prove because it is examinable. So anytime I see a tangent, mind you, know the definition of a tangent. The line does not cut through. Tangent and chord. We have a tan-chord. So let's prove this quickly, and then we have one more theorem to deal with. I hope you've drawn that. Circle, tangent, and the chord, and those angles are equal. All right, let us prove. We want to prove. Let me divide my board into two and create the question. So we have a circle. There we go. We have the center of the circle. We actually need that. We need that. There are two ways to prove this, but I'm only going to do one. So let's have the tangent here. We have that. We have this. And we have that. Okay. A, B, and C. We want to prove that angle DAB should be equal to angle C. Angle DAB is equal to angle C. That is, this angle must be equal to that angle. That's what we want to prove. We would need to do a bit of a construction. All right? We would need to do a bit of a construction. Remember what I told you earlier on in one of the videos. If I need to work with angle C, do not construct over C. Here is what I'm going to do in terms of the proof. Construction. Check what my construction would look like. Check what my construction would look like. I would construct a diameter. So this is O, right? My focus is on A and C. Okay, so please, I want you to watch what I am going to do. In fact, let me draw the circle afresh so that it's clear. I want to leave the question. I want to draw a new circle. We have a tangent. We have B, we have C, and we have that. Okay. And we have the center of the circle, which is O. This is D, A, we have B, all right, C. So watch what I'm going to do. Okay, let's put E here because it's a line. Now, here's my first construction. I want you to see what I'm going to do. I am going to draw a diameter. it must pass through the center. Remember, it's a diameter. It must touch the circle. It must touch the circle. So I can call this point A, B, C, D, E. Let's call this F. So construction. Draw diameter AOF. Remember, my focus is on C, right? Then I am going to join B and F. Remember that whatever construction I'm doing, I use dotted lines. Beautiful. Let's call this 1 and let's call this 2. All right? Let's call that 1. Let's call that 2. Let's call the B1 and B2 just for identification. Now, do you notice that this here is a tangent and this here is a radius? Oh, we just came from a theorem, all right, that says that this thing here is actually 90 degrees, 10 rad. We are going to need that particular information. All right, so we want to prove. Now, let's work with the proof. I'm done with my construction. What is my proof looking like? A1 plus angle A2 is actually going to be equal to 90 degrees. What is your reason? Radius is perpendicular to tan. That's the reason. Or tan perpendicular to radius, whichever one comes first. There's no rule. Now, watch. So that's the first thing, right? Now, watch the second condition. We have a diameter AOF. Oh, it means that B1 plus B2 is also equal to what? 90. So FBA is 90. Angle in a semicircle. Let me go mark that point for you. This is 90. Right. That is 90. That's our second step. Now, what do you notice? We can therefore get angle F because we can talk about a triangle. Angle F, therefore, will be 90 minus A1. 90 minus A1. What would be your reason? Sum of angles. I want to go back there in a triangle in case you didn't see what I just did. We have a triangle here. That's a triangle. Remember, this is 90 degrees. I know this as A1. So this is 90 minus A1. All right. Now we're going to bring in about 3 theorems here. About 3 theorems. Do you notice that angle F, let me use a highlighter, angle F is equal to angle C. Why? Angles in the same segment. Check, they are both coming from AB. We looked at that. All right, and the same AB. Oh, it means that angle F is equal to angle C, which is equal to 90 minus A1. What's your reason? Angles in the same what? Segment. Okay, we are almost there. So I now know that my C is 90 minus A1. But what is A2? Look at this. Remember, A1 plus A2 equals to 90. What is A2? A2 equals to what? 90 minus A1. What do you notice? That angle C, therefore, which is 90 minus A1, is the same as A2. Oh, angle C is equal to angle A2, which is 90 minus A1. I've added a few things just to make it clear. What is angle A2, by the way? Angle C. A2 is, where's my highlighter? Look at where A2 is. A2 is DAB. A2. DAB. This angle is therefore equal to that angle. We are done. DAB. Proof is done. This is called the tan-chord theorem. The tan-chord theorem. This is the approved proof. There are other ways of proving this, but this is our approved proof of the tan-chord. I could do this proof in a different way, but this is our approved theorem. Please take note of that. Take note of this. Tan-chord theorem. So number one, we looked at tan rad. Number two, tan-chord. We actually have a third one. We have a third one on the tangent. So with tangent, we're doing three things. Tan-chord, tan rad. Now we have the third one, which is tangents drawn from the same point. I hope this proof is okay. Please, this proof is examinable. Never forget that. This proof is examinable. Let's look at the third one quickly. So pause the video and write the notes. If I'm moving too fast and you've not written down the notes, just write down the notes. But let's go over it again, a quick voice over. Construction, you draw that diameter. Once I see a diameter, I see my 90 degrees there, right? Lovely. Now, radius and tangent, another 90. Now, if I look at this triangle here, this angle F will be 90 minus A1. Okay, so when I get my F, I see this and this are equal. So this is 90 minus A1. And A2 is also 90 minus A1. So they are equal. The angle between a tangent and a chord is equal to the angle subtended by the chord in the alternate minor major segment. All right, that is done. Number three, when it comes to tan, would have a summary of this. Number three, when it comes to tan, this one as well, we don't need to prove, we just need to know it. All right, two tangents, that's the theorem. Two tangents drawn to a circle from the same point outside the circle are equal in length. Two tangents drawn from the same point. What's our reason? We're going to say tangents drawn from same point. They are going to be equal in length. Tangents drawn from same point. Let's look at what it looks like in terms of the diagram. Okay, we always want to just highlight the center of the circle there. So I'm going to draw a tangent from here. And I'm also going to draw a tangent from here. A, B, C, D, and E. What we are saying is AB is equal to AD. Just that part. Tangents drawn from same point. Tangents drawn from the same point. This is very important as well. So this is our third theorem on tangents. And if I could make this a bit nice, we could actually draw, I wanted to see something beautiful. That's a radius. That's a radius. Oh, nice. Do you notice we have a kite? That shape is a kite. This is 90 degrees. Wait, it simply means AB. There's a lot of things that we are going to create, excuse me, from here. ABOD is a cyclic chord. We're going to be talking about this later on, all right, when I look at my rules. And I'll show you what we mean by converse. Why is that a cyclic chord? Because angle B plus angle D is 90. But don't let's put too many things at this point. So we are simply looking at tangents drawn from the same point are equal in length. Tangents drawn from the same point are equal in length. That's very key, and I hope that is well taken. So for tangents, we look at three things. Number one, tan-chord. Number one, we looked at, tan-rad. Tangent and radius are perpendicular to each other. Number two, we looked at tan-chord. The angle between a tangent and a chord is equal to the angle subtended by a chord in the alternate segment. Remember, minor and major segment. And that's the proof, which is examinable. Number three, two tangents drawn to a circle from the same point are equal in length. We are done with T. Now we look at our plus one. Oh, before we look at plus one, let's answer a few questions on tangent. Quickly, let's answer a few questions. Oh, I notice that this is a radius. That's a tangent. That's 90 degrees. You've got to state all of that when you write. Angle B equals to what? 90 degrees. Tan perpendicular to radius. Which means X is 90 minus 35, 55 degrees. Sum of angles in a triangle. We're done. We are done. Let me make this bigger, because I know you cannot zoom. There we go. So that's my radius again, and that's my tangent, and the angle between them is 90 degrees. Let's look at this one. We're looking for the value of A. Again, radius, tangent, that is 90. What are we saying? Angle B is equal to 90 degrees. What's your reason? Tan perpendicular to radius. Therefore, 2A plus 3A plus 90, if you want to add that, will be equal to 180 degrees. Sum of angles in a triangle. Simply, we know that 5A will be equal to 90. And what is A? 90 divided by 5 will then give us 18 degrees. Am I right? Yes. 90 divided by 5 would give us 18 degrees. I hope that makes sense. So you've got to write all your reasons and statements that you used in getting your answer. I hope that makes sense. So you can pause the video, draw the diagram, quickly sketch it out, and write the solutions to it. Because I think I have about 5 questions on this that I'm just going to play around with. And they get complex as it goes. All right. Let's see. We're looking for X and Y. Oh, sweet, sweet maths. Identify the lines. That's a tangent. That's actually a diameter. All right. But this is a radius. Do you notice that's 90 there? Okay, let's start from that. Angle B equals to 90 degrees. Tan is perpendicular to radius. Therefore, X is 50 degrees. Does that make sense? Beautiful. Now, look at this. The angle between the tangent and a chord. Which chord is this? Chord BD. Oh, I see that BD actually goes to the alternate segment and forms M. Therefore, M must be equal to that. We're done. Sweet, sweet maths. M is equal to 40 degrees. Tan-chord. And what is Y? Y is 90 degrees. angle in a semicircle. I don't know if you see the diameter there. That's my diameter. And it makes sense. Let's see if it's going to work. We got x to be what? 50, right? M we got as 40. Oh, that actually gives us 180. You see, it works. 40 there, 50 there, that's 90, plus 90, 180. Perfectly works. Perfectly. It works perfectly. So, please, you can sketch the diagram quickly in your books so that it makes sense. All right, let's look at this. What are we looking for? We're looking for x and y. Let's identify. I have a tangent and I have a chord. So this is the angle. Does this chord go somewhere else? Chord BC. Oh, I see that it subtends angle y. So therefore y is equal to 60 degrees. And what's my reason? Tan-chord theorem. Okay, it's going to be easy now. I'm going to write my 60 there. I'm looking for x. Ooh, but I see something very lovely. X is in a triangle. And I see, oh yeah, this takes us back to radius. Once you identify, oh, angle at the center. Oh, there's so many things to do here. So angle at the center is 2 times angle at the circumference. Remember, the one in the middle is always the bigger one. Oh, great. So can I say angle O1 equals to 120 degrees? Angle at center is equal to 2 times angle at circumference. Then C1 is equal to x. Angles that are opposite. Do you notice all of this we said before? Now, so this angle here is 120. It means x is what? 30. Sum of angles. How did I get that 30 though? How did I get the 30? 120 plus x. Remember, this and these two are equal. So we say 180 minus 120 divided by 2. 60 divided by 2 would give us 30. Beautiful. There were so many points to write down before getting our values. All right. When I'm done, guys, in our next lesson, I'm going to then give you tips. A few things I'm going to do there before I look at any activity. Tips on finding your angles quickly and when to use your converse. Okay, we're going to discuss that. I have just a few minutes allocated for this particular session. Okay, let's look at this. I see a lot of things going on here. Oh, I also see parallel lines. Okay, so they're mixing a whole lot of things. I see fun angles. I see tan-chord. Wow, so many things going on. Okay. Which one would we get first? I think we're going to have to get y first. Why? Let's see. Learn to write the label the lines. That's a radius and a radius. This is angle at the center. Ah, do you notice? I already have that now. Angle at the center is 2 times angle at the circumference. The bigger one is the one in the middle. So what is your y? Y is 70 degrees. Y, angle at center is equal to 2 times angle at circumference. Everybody good there? Good. And the secret again, like I'll be doing in my next lesson, because I'm the one doing all of these questions now. 70 degrees. I write what I found. Okay, let's go check something here. Look at x. Let's label. There's a tangent there, and there's a chord. Oh, definitely we have to look at a tan-chord theorem somewhere. Okay, let's go check. Where's my highlighter? Tan-chord. This is in the minor segment. We need to look for the angle subtended by the chord in the major segment. So x is equal to 70. Reason, tan-chord. We're done. X is equal to 70 degrees. Tan-chord. Okay, let's write it there. 70 degrees. Our job is now to look for M, which is going to be quite an interesting piece to find. But let's see, we have to get it. There are parallel lines somewhere. What is this parallel line going to help us with? Will it help us with anything? Let's see. Will it help us? I've got this line. We're told it's parallel to that line. It's actually going to help us. Do you notice? It's a Z. Alternate. So this angle is 70. Oh yeah. And we're done. I see that we're done. This is still the tangent, right? This whole thing is 90. This is 70. Obviously, you can now get the value of angle M. Beautiful, beautiful connection. So let's start by saying ABC is 70 degrees. Alternate what? Angles. But don't just tell us alternate angles. All right? Don't just tell us alternate angles. You must tell us the lines that are parallel. CD is parallel to AT. Now, ABO is 90 degrees. Tan perpendicular to radius. Therefore, M equals to 20 degrees. We can see that has no reason. 90 minus 70. That's just maths. 90 minus 70. And we are done there. That's how it works. Lovely question. So you've got to keep checking. But like I said in the last lesson, I will be showing you how to get things done. I think I'll do the last theorem and then show you, so that it's not too long, how to get this thing so easily. Okay. I think I have one more question. Oh, that's it. Yes. So that's going to be it for our lesson today. Remember, tangent. We looked at two things, P and T. P, parallel lines. Tangent, three things. What did we look at? Tan-rad, tan-chord, and tangents drawn from the same point. Our last lesson will then be looking at theorem number 1, and then we'll look at the other things that go along with solving your questions easily. Things like converse, things like how to find your angle so easily. It's a lot of fun. Please make sure you write the notes and go through again. So you go through in different pieces and put the whole thing together in our last lesson. And from there, we jump straight to activities. All right, that's my lesson 4. And we have lesson 5 coming up next shortly. Goodbye, everybody, and have a lovely evening.